What if curiosity itself could be learned? In 2018, researchers at OpenAI asked a deceptively simple question: how do you teach an AI to explore? Most reinforcement learning algorithms rely on rewards, signals that tell the agent when it's done something right. But what happens when rewards are sparse? When the environment goes silent for hundreds, even thousands of steps? Enter Montezuma's Revenge, a 1984 Atari game that became the Mount Everest of reinforcement learning. 24 rooms of traps, keys, and locked doors. For humans, it's a challenging puzzle. For AI agents, it was a graveyard of algorithms. By 2018, the best algorithms could barely explore 6 rooms. Random exploration was useless. The first key alone requires navigating past enemies and down ladders. The probability of stumbling upon it by chance? Astronomically low. Chapter 2, The Noisy TV Trap. The intuitive solution was simple. Reward curiosity. If an agent can't predict what comes next, that's interesting. Give it bonus points. Early methods used prediction error as intrinsic motivation. Encounter something surprising, high reward. Encounter something familiar, low reward. But prediction error curiosity has a fatal flaw. Imagine an agent that discovers a television showing static. Random noise is maximally unpredictable. Forever. The agent becomes hypnotized, watching the static for eternity, earning infinite intrinsic reward while learning nothing useful. This is what researchers call the noisy TV problem. But it's just one of 4 fundamental sources of prediction error. First, truly novel states that deserve high curiosity. Second, stochastic transitions, randomness in the environment that can never be predicted. Third, model limitations, errors from using a neural network that lacks the capacity to model complex phenomena. And fourth, training noise, inherent variance from stochastic gradient descent. Chapter 3, The Breakthroughs. The R&D insight was counterintuitive. Instead of predicting the next state, predict the output of a fixed, randomly initialized neural network. Take any observation, pass it through this frozen target network, and try to match its output with a separate predictor network. The prediction error becomes your curiosity signal. Why does this work? The target network is deterministic. It always produces the same output for the same input. On familiar states the agent has seen many times, the predictor learns to match the target perfectly. Error drops to near zero. But on novel states, the predictor hasn't been trained on similar inputs. Error stays high. The researchers validated this with a beautiful experiment. They trained a predictor on MNIST digits, handwritten 0s through 5s, then showed it fashion MNIST images, shirts, shoes, bags. The predictor had never seen clothing items. Result? High prediction error on the novel class, exactly as the theory predicted. Mathematically, this connects to counting-based exploration methods. Under certain assumptions, R&D error approximates the inverse square root of the visit count. States visited many times get low bonuses. Rarely seen states get high bonuses. But unlike tabular counting methods, R&D generalizes across similar states through the neural network's learned representations. Chapter 4, Engineering for scale. Intrinsic rewards create a subtle problem. Traditional RL treats each episode as independent. The agent should explore as if it has never seen the environment before. But intrinsic rewards are non-stationary. They diminish as states become familiar. This creates a conflict. Should the agent maximize returns within an episode or across its entire lifetime? R&D's solution was elegant. 2 separate value heads. One estimates extrinsic returns, treating each episode as a fresh start. The other estimates intrinsic returns across the agent's entire lifetime, never resetting at episode boundaries. The policy learns from both, combining short-term game rewards with long-term exploration incentives. The discount factor also required careful tuning. Extrinsic rewards use a standard gamma of 0.999, almost no discounting, encouraging long horizon planning for game scores. Intrinsic rewards use 0.99, or more discounting, encouraging the agent to seek novelty sooner rather than later. Finally, observation normalization proved critical. Raw Atari frames are normalized by running estimates of mean and variance. This keeps the target network's outputs in a consistent range, preventing the intrinsic reward signal from exploding or vanishing as the agent explores new visual territory. Chapter 5. The results. First, the researchers tested pure exploration, no extrinsic rewards at all. The agent explored using only curiosity. Compared to other intrinsic motivation methods, R&D explored dramatically further, reaching areas of Montezuma's revenge that previous methods couldn't touch. With both extrinsic and intrinsic rewards combined, the results were striking. R&D achieved a mean score of 10,000 on Montezuma's revenge, more than double the previous state of the art. It explored 22 of 24 rooms, occasionally completing the entire first level. For the first time, a reinforcement learning agent exceeded average human performance on Montezuma's revenge without any demonstrations. The simple insight, predicting random features, had unlocked a door that had resisted algorithms for years. Why did dynamics-based methods struggle where R&D succeeded? Predicting next frames requires modeling everything: game physics, enemy patterns, visual details. R&D only requires recognizing, have I been here before? Perhaps most surprisingly, the R&D agent developed what looked like intentional backtracking, returning to previously visited states to reach new areas. Goal-directed exploration emerged from simple prediction error. The key insight: don't measure novelty against a moving target. Measure it against fixed random features. Curiosity needs a compass, not a destination.